Okay, all right, so the last part of this class, I want to show you the actual implementation of CNN using TensorFlow. And as you can see, I'm going to compare it with the ANN, with the same data input. And you can see how efficient it is. And that's the beauty of it, okay? So we're going to go through, I'm not sure you have to use the code that I sent you in my website. So it's going to be this one. So 2, AI class. So CNN, so go to the code and make sure that you copy this one to your Google Drive and open it from there. Okay, so while you're doing that, you can listen to my demo right here. You can see my demo. So I'm working first on the file called C1 ANN baseline. So I want to establish the baseline of what that ANN can do and what is the computation, like what is the parameter size and things like that. So in my ANN, so this one I'm using the MNIST data, but I'm using the reduced data. So instead of using 60,000 image, I'm only use 2,000. So this is very, very small, just to make sure you can run it in a reasonable amount of time. So essentially the beginning is the same. I'm loading the data. Note that I actually divide the data by 255. So that is the number, that is the grayscale level. The grayscale level goes from 0 to 255, but I want to make sure that everything gets squashed to 1. Because usually neural network doesn't like anything larger than 1. So I squash it to 1. Doesn't really matter. You can always do this to your input, okay? And then I only choose 2,000 picture. So the variable called reduce dimension is just to make sure that I don't use 60,000 images. I usually use 2,000. That's all. Okay. And then when I build the model, this one is the ANN, just the regular good old ANN architecture. So I use the shape of 28 by 28, so that's the input, the size of the image, and then I flatten so that it's just a vector. And then I use the dense layer, so that the hidden layer, one hidden layer with 128 nodes with a ReLU activation function. And then the output is going to be 10 because I want 10 classes. That's all. So this is similar to what we used previously. Okay? And I'm going to compile them with atoms. So that's the go-to optimizers. Sparse categorical cross entropy is the loss function. And then I use the matrix, the accuracy. I want to track the accuracy during the fitting. Okay, and I'm going to train them for 40 epoch. So let's go. Let's see how long it runs, and Oh, and also with this set of parameter, I'm looking at 100,000 parameter. So that's quite a big model. And you might see that it's actually takes some time to train, right? It's not instantaneous at all. And keep in mind that this is only 2,000 images though, not 60,000. Okay, so if it's 60,000, it will be a lot longer. All right. So with this set of training as a parameter, I can see that my training history is like this. Okay. So the loss, actually the accuracy kind of goes up pretty high, right? And my evaluation tells me that I got something about about 90% accuracy. So keep in mind that I don't train everything to the fullest extent. I just kind of train things in a rather quick way. So to set a benchmark, so this is about 90% accuracy, okay? And then I can also do do the softmax function. I look at the softmax output to see what the network is predicting versus the real picture. And also, I'm just gonna, just look into the picture that the network gets wrong. So this is the same thing as I did before. It's nothing different, right? Okay. So I want you to compare this with CNN. Okay. So for the CNN, it's like this. All right. So first, I'm going to load the model. So let me load it. And then this one, I'm just loading the data and then scale the data to 1. Because the network always like number 1, or like maximum of 1, okay? And then I'm going to show that the my original image I have 60,000, right? But then I'm gonna reduce everything into 2,000 images. So this part, I just pick 2,000 images from my training data, okay? And here's the part where we construct the CNN, okay? So that's the difference. So first, let's look at the architecture. So we're gonna start our layer, not the dense layer anymore. We're gonna do the convolution layer. So this part, think about filter that scan through the image, okay? With different size, you can specify what the size is, how big is that scanning matrices, right? And then the stride is do you skip any blocks or in certain directions? And what is the padding of your input, okay? And then I'm gonna follow them with max pooling. So max pool just detect just the maximum value in particular regions, and that keep things even smaller in terms of the output size, make things faster. And then I'm gonna include the dropout layer so that during the training, the model is forced to learn different way of connecting the layer so that it's even more, I guess, challenging for the model, okay? In order to do that, I'm going to construct the model like this, okay? So the way that I construct this is a little different, okay? Because in the ANN, I do everything in one line. And that's okay for ANN, like this is one line, right? But in CNN, it's gonna get really, really long. So I wanna break things into multiple lines of code. And I can do exactly like that by just saying that first, I wanna construct just the blank model. So this one saying that this model is gonna have multiple layers, but I haven't specified any layer yet. And I just keep adding them later, see? The third line, I guess here, would be to add the input layer with the size of 28 by 28 by 1. So notice that now my input is no longer 2 dimension, it's actually 3 dimension because we need the channel. Even though we only have one channel, we need to specify the third dimension so that it kind of aligns with how CNN work, okay? And then I'm going to add another layer, so model.add, and this one is called conv2D, so convolutional 2D, with the number of filter of 32. So that means that my output layer is going to be in dimension of 32 in depth, okay? So I have 32 orange blocks, if you were to remember my lecture, okay? And each of the orange blocks will be the size of 5 by 5, so it's going to be, small compared to the input shape, right? The stride of 1 and 1, meaning that when I do the scanning, I don't skip any blocks at all, okay? And padding same, meaning that I want the output to have the same dimension as the input. So that means that my output should have the output size of 28 by 28 by the number of filters. So 28 by 28 by 32. That would be my output size, okay? And the data format, this one doesn't really matter because we only have one channel. But if you want data format, there are ways to specify the order of the, I guess the order of the color or something like that, okay? This one is not, doesn't make any difference in here. Okay, so I add the convolution layers and then I add the max pooling. So this one is gonna keep things smaller. So my output is gonna be even smaller, I guess because of the way that this one works, okay? And then I add another convolution layer. So this time I do 64 filter. So that means that my output is gonna be even more deep because it has 64 orange boxes, right? Each of the box is 5 by 5 with stride of 1, same padding, okay? And then followed by another max pool. So this one is gonna keep things down even more. So it's even smaller in terms of width and height, but very, very deep, okay? And now followed by the flatten. So flatten meaning that make everything from 3-dimensional layer into just a vector. So the node is just a node that are just spread out, flatten. And then I followed it by the dense layer, so the 32 nodes, okay? And some drop out, and then followed by the last layer, which has the unit of 10. So this one is essential because I want 10 classes. Again, this one you cannot change. The rest you can change. Like everything in between, actually you can feel free to change it. But you gotta keep things a little bit in, kind of keep track of, if the number makes sense or not, okay? So if I were to run this, and I do the model summary, these are the layers that happen in my convolutional model, okay? So as you can see that right now, my convolution is very, very small, right? It's only like about 1,000 parameter. The next is, it's significant, but it's not that much, right? 50,000, right? As you can see that my dense layer is actually quite a lot. So this part kind of blows up, right? So in the end, this one, I end up with 150,000 parameter, okay? Since, as you can see that this one is actually larger than this one over here. But actually this one only has, just, like a really small, like this, right? But you can kind of combine this one later. Like if you want to be smaller, you can change this one to be maybe 16 or something, it will be smaller. But I want to keep it like this right now, okay? So this one is 152, and then I want to compile them with atoms, and then the same loss function, and I'm going to run it. Okay, done. So it does take some time, right? It's not instantaneous by any means, okay? All right, so we're going to have to do, check out the training data, so the history, right? So we're going to look at the graphs a little bit more, okay? As you can see that we can make this one, the loss goes down, accuracy goes up. Again, we can do more. Right? If you want more, you should increase the number of epochs, because if you like, the accuracy can go up a little bit more, right? And in the end, we got something around 0.9. So, with just the beginning batch that we're doing, actually we are getting a better results than just the pure ANN, okay? And these are some of the misclassification that happened, okay? So I guess I guess my comparison is not fair in a way that ANN, if you need more performance, you need to increase the architecture even more. So this one is too simple, I would guess. You need to make it a little bit more in order to beat the CNN. So CNN is actually quite efficient compared to the performance. I guess that's what I want to say here. So if I were to fit it, like make a fair comparison with ANN, so right now it's not doing as well as CNN. But I can certainly come back here and increase the layer complexity, so maybe more layers with a larger number of neurons. And then you can see that ANN can also increase the performance with the performance, increase the accuracy, although with the computational performance hit. Okay? But CNN is also certainly is more efficient if you were to compare with like a similar complexity of the model. That's what I would say. Okay. Okay. So feel free to play around with the layer, changing the number of nodes and increasing the number of convolutional layer. Feel free to do that. For example, if I want to add maybe just another more, then I can just do this. I can just do more convolutional layer like this, adding more here, right? So maybe this one I want to do 5 by 5, so okay, conv 3, and then do another max pool. Usually max pool is follows the convolutions, and that one. If I were to run this one again, I think I will get some. Oh, I cannot use the same name. So pool 3, like that. There you go. So this model is actually even higher in terms of parameters. Okay, so something like that. It looks, whoa, this one even better actually. So I get something about 0.95, so about the same accuracy, but actually my training matrices actually looks better. So certainly increasing more layer in my convolutional pipelines actually helps. Okay, so something like this, it's used a lot nowadays in terms of like image classification. Okay. Okay, and with that, I want to end for today for now. But next time, I want to show you some of the work or some of the milestones that has been done called CNN architecture. And if you want to do the image classification today, there's so many things you can choose from. But at least there are certain milestones or certain type of models that has been developed ever since the first. It was created in 1998. So a little bit more next time, and then hopefully we can do the language model, which is something I want to teach for so long. So hopefully our last class will be more fun and more recent in terms of the technology. Okay, thanks a lot, man. See you next time.